Okay, lesson 4.3, maximum and minimums. Let's take a quick look at this here. Now, what we study here is values of functions that are at extreme points, and we call those extrema. So we're talking about maximums and minimums. And of course, again, in many of these situations here, we don't have context. We don't have like a story associated with it. But I need you to imagine again that we have functions that describe things that happen in our world. And many times it's these extreme values that we're really interested in. What happens when our function has reached some maximum value, or what happens when it's reached some minimum value? What's going on with its rate of change at those times? And so we're interested in, again, thinking about that. And we call this sometimes, or many times we call this optimization problems. So looking at this first kind of situation, you get an example here of a continuous function here, and you see that there is some value that is the lowest, and that would be called the absolute minimum. And again, we're talking about extrema as we think about it in that term. Extrema represents a minimum, or it also represents a maximum. And so, of course, it's important to look at the definitions. Definitions are always important in calculus and mathematics and science, because this gives you the precise language and the precise way that we're defining these terms that we use. And so you can see in this definition, you'll have a maximum or minimum, right, over some interval, given that, right, as it sees here, we say f has an absolute maximum on some interval, right, the domain of a function, at C if f of C is greater than or equal to all f of x. And that should make some sense. So read that and then take a look and think about that and make sure you understand that language. And the same true for minimum, right? There's a definition. What does it mean to be small, the smallest? It means that for that value, you're less than or equal to all the values, right, within that. And hence we would call that the absolute extremum or minimum. Here are some pictures of how that could occur within functions in graphs, piecewise functions, functions with asymptotes. As you can look, at some point, you will have maximums and minimums at some point potentially, right? As you look at this here. And so you can see in the figures, you see several functions with different possibilities regarding absolute maximum. In this case, this will go on forever. So it'll be an infinite value. There's going to be some value that's greater than all the other values. Now we have something called the absolute value theorem. The extreme value theorem guarantees that for a continuous function over a closed interval, over some closed interval, and that's the key, right? That there is some closed interval over which the function is defined, that we have a maximum or minimum. And so you can see that over some closed interval. You also see it could happen with piecewise functions, or functions that are non-traditional or only defined over some smaller interval. And hence the extreme value. If you have a continuous function, that's the key for the extreme value theorem, right? There is a point that will always be the maximum, and there is a point that will always be the minimum. This leads us to another important term we use is critical points, right? We have these critical points, and we want to go ahead and define what a critical point is. But again, it's going to be related to where are these maximums and minimums. And so we introduce another term, local extrema. So sometimes we only care about a certain smaller interval inside of the entire domain. So for example, here, this is the highest value, the absolute maximum, but here would be a local minimum, or local maximum. Close to within this range, it's the greatest value within there. Here's your definition as we take a look at function has a local maximum at C if there exists an open interval, right? Again, back to that for every value, right? For every value, local maximum, for every value, f of C is greater than f of x. So again, that back to those definitions, which leads us to finally this critical point. And so we're going to be using this language in this section and continuing on. If C is some point inside of the domain, we say that C is a critical point if f prime of C, the derivative at that point equals 0, or it's undefined. So if that occurs, if the rate of change is 0 or the derivative is undefined, we have a situation where we have a critical point, and then that will then lead to what we're going to then discuss. What do we do with those critical points, right? And it's here. If f has a local extrema at C and f is differential C, then we have f prime of C equals 0. So if we know there's an extrema, max or min, and it's differentiable, we know the derivative equals 0 at that max or min point. That leads us to looking at this here, looking at the different ways we can have critical values, where they would be, critical points. F prime of C equals 0 here. Here it's undefined. We have an extrema. There's an extrema here. Remember, with an absolute value, it's undefined. Here we have this point of inflection here. This point of inflection, which we'll be talking about, where the derivative is 0. So it increases, it slows down, and then increases again. There's no local maximum or minimum here, but we have this behavior where f prime of C equals 0, and then here undefined as you have that vertical asymptote there. So what we end up doing is we're going to use these critical points to find absolute extrema, the max and min points for a function we have. And so there's a process. So you want to make sure you understand that this process. I would emphasize this point here, right? If you have a continuous function over some interval, to find the extrema, you're going to evaluate those endpoints. So those endpoints matter, right? Because we can't take the derivative at those endpoints. And then you find the critical points for all of those over A and B. Okay, and then so that means you're going to set the derivative equal to 0, or you're going to find out where the derivative is undefined. And then that will allow us to find, right, critical points, and then we can compare and find out if those are absolute maximum or minimum. So you're going to do this a lot in this course, or at least in this chapter, where we take the derivative of the function, set it equal to 0, or determine where it's undefined. And then from there, we're going to determine by plugging in values to if it's a maximum or a minimum. So you want to make sure you go through this example here for that. And you could determine that. So that's going to be the process we do. You end up with a lot of interesting kind of algebra. So don't be afraid when you encounter that. Like, see how you take the derivative of this function. You'll see something like that many times. Again, when you set it equal to 0, there's a cancellation. So you can see this part here comes up. So don't be afraid of the algebra. Take a look at those. You may end up with some rational exponents, so you have to deal with. But you don't want to be afraid of those, okay? So that's our review for 4.3.